Hello everyone, welcome back to the channel. Today we are diving into a truly elegant and challenging problem from the 2003 Putnam exam, problem 3. So this is the 64th Putnam, and first I'll give you a little context about the exam. The Putnam exam is one of the most prestigious undergraduate mathematics competitions in North America. It features problems that require creativity, insight, and mathematical maturity. Many of those same ideas show up in high level competitive settings here in India, and especially in the preparation of JEE and other advanced test series. So, although the Putnam problem is aimed at university students, the underlying techniques are very relevant for ambitious JEE aspirants, not only because they force you to think outside the standard patterns, but also because you will see similar structures in the coaching test series time and again. So now the focus of the day, the problem statement. So let us look at the problem statement. The problem statement is quite simple. You just have to find the minimum value of this particular expression. All right. So the expression that you have is the summation of all the trigonometric ratios, all 6 trigonometric ratios, and there is a mod over here. All right. So the modulus of sin x plus cosine x plus tan x cosecant x plus secant x plus cot x. So you have to find the minimum value of this particular expression. So let us go and solve this question. So let us consider this quantity as p. So now p can be written as sin x plus cos x plus tan x can be written as simply sin x divided by cos x plus cosecant x is 1 by sin x plus secant x is 1 upon cos x plus cot x is cos x upon sin x. Now let's do something. So let us say this is sin x plus cos x plus, let's take the LCM here. So it is sin x multiplied by cos x. So this will be simply sin square x plus cos x plus sin x plus cos square x. Now sin square x plus cos square x is simply 1. Alright. So this is sin x plus cos x plus 1 plus sin x plus cos x divided by sin x cos x. So whenever you see the sum of sin x plus cos x and the product of sin x and cos x, you should always remember this particular identity. Sin x plus cos x whole square is equals to sin square x plus cos square x, which is 1 plus 2 sin x cos x. So now we can do two things. We can replace sin x plus cos x with the square root of this particular quantity, or we can replace sin x cos x with the whatever we find from here. All right. So let us find out. So it is, since it is difficult to work with square roots, so let us find out what sin x cos x is. Sin x cos x is sin x plus cos x whole square minus 1 divided by 2. I wrote this thing from this. Alright. So now let us assume sin x plus cos x is equals to a. Then your sin x cos x is equals to a square minus 1 upon 2. Alright. So your p can be written as, so first you have sin x plus cos x, which is a, plus 1 plus sin x plus cos x, again that is a, divided by sin x cos x. So that is a square minus 1 by 2. So this is simply a plus 2 multiplied by 1 plus a divided by a square minus 1. So we have a square minus 1 in the denominator. So that is simply a minus 1 into a plus 1. Alright. So now, so let us see what a is. So a is sin x plus cos x. So So this can be written as, let us multiply it with root 2 and divide it with root 2, the entire expression. All right. So this is cos 45 and this is sin 45. So it is in the form of sin A cos B plus cos A sin B, which is sin of A plus B. Alright, sin of x plus pi upon 4. So this is your A. Now what you can do is, the reason why I have done all of this is to show that you can safely cancel A plus 1 and A plus 1, because if A is equals to, you can do the cancellation only when A is not equals to 1, sorry, minus 1. You can do the cancellation only when A is not equals to minus 1. If A is equals to minus 1, so this quantity and this quantity both will be 0, and 0 by 0 form you will get, which is an undefined form. So A should not be equal to minus 1. So let us say when A is equals to minus 1, let's say A is equal to minus 1. So from here you can write minus 1 by root 2. From here I am writing is simply sin of x plus pi by 4. So this is simply x plus pi by 4 will simply be is equal to minus pi by 4. So this is sin of minus pi by 4. So this is minus pi upon 2. So which is minus 90. Alright. So if you put minus 90 here, the tan function is not defined. Yes or no? The tan function is not defined. So it will approach infinity. Similarly, the secant function also will approach infinity. So we should not take x is equals to minus 90. So that value we should not take. So that is same as saying A will not be equals to minus 1. Alright. Alright. So in order to find the minimum value, if we have to find out the minimum value, that minimum value has to be finite. But if you take A is equals to minus 1, that this value approaches infinity. So the problem statement becomes redundant. Hence, we should not have A is equals to minus 1. Only after you do all of this reasoning, you can cancel out these terms and write P as A plus 2 upon A minus 1. Alright. So P is your A plus 2 by A minus 1. So let us proceed. A plus 2 upon A minus 1, and your A is root 2 times sin of x plus pi by 4. Now you have to find out the minimum value of mod P. So let us go and differentiate P. So this is a very standard approach now. So dP upon dA. So that will be simply 1 minus 2 upon A minus 1 whole square. So let us set the derivative to 0 to find the turning points. So that will give you A minus 1 whole square is equals to 2. So your A will be 1 plus or minus root 2. So you got two values for A. But if you check here, the maximum possible value for A, maximum value of A is root 2, and the minimum value of A is minus root 2. So these are the only allowed values of A. So the values outside this range are not allowed. Alright. So here if you consider A is equals to 1 plus root 2, this goes outside the range. So A lies between minus root 2 and plus root 2 from these two things that we have derived. So this goes out of that range. So this is eliminated. So the only root will be A is equals to 1 minus root 2. So this is the only turning point of the function that we have. So this is the function that we have in terms of A, and the only turning point of the function is 1 minus root 2 inside this particular range. Alright. So let us try to draw the graph of the function. This is not needed. The graph is not needed to answer this particular question. But if you do all of this analysis, it will really be helpful for you guys. So let us draw the graph. let us say this is the axis. So this is minus root 2 and this is plus root 2. So at a is equals to minus root 2, if you put a is equals to minus root 2 in this, you will get a is equals to minus root 2. If you put that, you will get p is equals to 2 minus 3 root 2. Similarly, if you put a is equals to root 2, you will get p is equals to, I forgot the value, so let me derive it, root 2, no? A is equal to root 2. So that is root 2 by 2 upon root 2 minus 1. Rationalize this term, root 2 plus 1, root 2 plus 1. So root 2 plus, so this is 1. You can apply a plus b into a minus b formula. So this is 2 root 2 plus 2. So this is 2 plus 3 root 2, alright. So when you put a is equal to root 2, this will be 2 plus 3 root 2. So this quantity is slightly less than minus 2. Alright, keep that in the back of your mind. So now let us try to plot the graph of this. So at a is equal to minus root 2, so here you have minus 2 and here you have 2 minus 3 root 2. At a is equal to minus 2, your graph is here. When you put a is equal to 0, okay, and your turning point will be at a is equal to 1 minus root 2. So 1 minus root 2 will lie, let's say somewhere here, 1 minus root 2, and let us say this is 1. Alright. Now at a is equals to minus root 2, your graph lies here. So let us put a is equal to 0 in this. If you put a is equal to 0 here, you will get minus 2. So at a is equal to 0, your graph lies somewhere here. Alright. Now, so your graph goes somewhat like this. And at a is equal to 1 minus root 2. At a is equal to 1 minus root 2, it will come somewhere here. It is increasing, so it will come somewhere here. Alright. Now this is a turning point. After this, it should go down. Alright. So this is 2 minus 3 root 2. So this point is 2 minus 3 root 2. So now it should go down. Where will it go? So to decide that, let us see. A is equal to 1. You should not put a is equal to 1 into this expression, because if you put a is equal to 1, this denominator will become 0, which should not happen. Alright. So a is equal to 1 will act as an asymptote. Alright. A is equal to 1 will act as an asymptote. Let us say we are approaching a is equal to 1 from the left hand side of a, 1 minus. So this is simply, so this term will be 1. So this tends to 0, but this term will be negative since a is approaching from the left side of 1. So this is 1 minus infinite, so which is negative infinite. So since the turning point is 1 minus root 2, it will turn here, and by the time it reaches 1, it goes to minus infinite. Similarly, if we are going to, if we are approaching 1 from the positive side of 1, that means the right hand side of 1, this will be 1. So this is 1 plus. So this will be 0. This whole term will be infinite, but it is positive infinite. So it is 1 plus infinite. So that will be infinite. So at 1, it will be at infinite, and it will keep decreasing and reach root 2. And at root 2, the value of the function is 2 plus 3 root 2. This is 2 plus 3 root 2. Now, what do we have to find out? So we have to find out the maximum value of mod p. So this is the graph of p. Now let us draw the graph of mod p. Before doing that, so let us find the value of p when a is equals to 1 minus root 2. Alright, let's do that. So a is equals to 1 minus root 2. Then p is equals to, so a is 1 minus root 2. So 1 minus root 2 plus 2 upon a minus 1. So 1 minus root 2 minus 1. So this and this gets cancelled. This is minus root 2. So 1 minus root 2 minus root 2. So 1 minus 2 root 2. Alright. So it is less than, so 1 minus 2 root 2. So where do you get that? So you'll get that somewhere here, 1 minus 2 root 2. Alright, so now let us go ahead and draw the graph of mod p. Alright, so let us draw the graph of mod p. So let us say this is A and this is mod p. Now this part of the graph remains same even when you take modulus. So this is a positive part on the graph, so this part will remain same. Alright, so let's do that first. So let us say A is equal to 1 is your asymptote. Alright, A is equal to 1 is your asymptote, and so this part of the graph will remain same. So this is, so this value is 2 plus 3 root 2. Now this part of the graph will be flipped, because if you take the modulus of this value will go and sit here. So if you take the modulus of this point, it will sit here. So if you take the modulus of this point, it will go here. So this will look something like this. So the mirror image of this with respect to x-axis, the mirror image of this in x-axis, when you take modulus, that happens. So let's do that and draw the graph of mod p. So this, let's say this is minus root 2. All right, and let us say this is 1 minus root 2. So at 1 minus root 2, here it is 1 minus 2 root 2. So here when you take the modulus, it will be 2 root 2 minus 1. Okay, and at 0, here it is minus 2. So when you take modulus, it will be plus 2. So 2 will be somewhere here, and when you at minus root 2, here it is 2 minus 3 root 2. So here it will be 3 root 2 minus 2. 3 root 2 minus 2. So at minus root 2 it is 3 minus 2 root 2, and at 0 it is 2, and at 1 minus root 2 it comes here, and here it was a maximum point, so here it will be minimum point. So it will go here and then it will go here. I have not exactly drawn the mirror image of this here. My graph is little bit messed up. So just think it is a line like this and it went like this. Okay, just the mirror image of this. All right, now we have to find the minimum value of mod p. So this is the graph of mod p. So therefore the minimum value is whatever you get at this point, which is 2 root 2 minus 1. So therefore min value of mod p is 2 root 2 minus 1. All right, I hope you guys understood this question. So if you have any queries, you can always reach out to me through the comments. All right, if you like the content that I'm making, do share it with your friends. Subscribe the channel for more such content. And if you like this session, do not forget to like the video. I'll meet you in the next video. Till then, take care.